In this lesson, we're answering the question, what does it mean to partition a line segment into a given ratio? Now, by now, you should be familiar with how to take a line segment on a number line and to be able to find a ratio that corresponds to parts of that line segment. What we're going to focus on next is being able to identify a point on a line segment that actually allows us to partition or divide a line segment into a given ratio. Let's take a look at partitioning a directed line segment. Now, a directed line segment is just a line segment that has direction. And we can actually partition or divide this up into parts given a specific ratio. A formula, the section formula, allows us to do just that. What it does is it actually identifies the coordinates on a number line of the specific point that actually divides it into the ratio that we want. Now, first, let's identify the variables that go to this formula right here. We have x sub 1, that represents the value of the beginning endpoint of our directed line segment, and x sub 2 is the final or the other endpoint. A to b is the ratio that we're trying to get. A over a plus b, the first value in our formula, simply represents a part to the whole in terms of the ratio that we're trying to get for our line segment. And x sub 2 minus x sub 1, well, that's just the length of the entire line segment. We then add the value of x sub 1 so that we can make sure that we're using that concept of direction. So let's go ahead and practice the formula with this example. We want to find point E on this number line down here that's between D and F such that it's going to partition directed line segment DF into a 2-to-1 ratio. Now I can just look and see that this line segment is 5 units long. And the thing about a line segment that's 5 units, it doesn't lend itself nicely to a 2-to-1 ratio. We're going to get a fraction instead of a whole number for our partitioned point. So we just need to keep that in mind. So let's go ahead and start plugging these values into the formula. Now it's essential to remember that this is a directed line segment. D is coming before F, so we're going in the direction of F. If we did it backwards, we'd get a wrong answer. So the value of D is at -3, so that's going to be x sub 1. And the value of F is at 2, so that's going to be x sub 2. And since we're looking at a 2-to-1 ratio, well then A is 2 and B is 1. So let's plug these values into our formula. All right, well, A is 2. A plus B would be 2 plus 1, or 2/3. Multiplying by the length of the line segment. Well, we already said the length of the line segment is 5, and that's found by taking 2 minus a -3. 2 minus -3 is the same thing as 2 plus 3, or 5. And then we're adding x sub 1, which is a -3. Well, 2/3 times 5, that's equivalent to 10/3. And if I take 10/3 and add a -3, it's the same thing as adding a -9/3 by getting a common denominator. And so what that does is gives us an answer of 1/3. That's that fraction we were looking for. So on the number line, that'd be right about here. So I can put E right there, and that actually divides our line segment into a 2-to-1 ratio. But we can actually check to see if that works. DE has a length of what? Well, -3 to 1/3, that's 3 1/3. So we could say that's 10/3 units. And E to F, well, that's 1 2/3, or 5/3 units. So what I'm actually doing is comparing 10/3 to 5/3. It's the same thing as comparing 10 to 5, or a ratio of 10 to 5, which in turn is a ratio of 2-to-1. So that does check out. So why don't you go ahead and use the section formula on your own with a different line segment. You've seen how to divide a horizontal line segment into a given ratio. Well, we can use that same reasoning in order to partition a directed line segment in the coordinate plane that now has both horizontal and vertical components. So the point P is going to be at x comma y, and that's going to partition the directed line segment from the first point, x sub 1, y sub 1, to the second point, x sub 2, y sub 2, in the ratio a to b, where x and y can be found by using these formulas. Now the first formula you'll recognize because we just used that when we were only focused on the horizontal change. But now that we have a vertical component, we need the y. So you'll notice that the x sub 2's changed to y sub 2, and the x sub 1's changed to y sub 1's. That allows us to find both the x and the y coordinate. Let's use this in an example. We want to find the coordinates of point P that's going to divide the directed line segment ST into a ratio of 4 to 1. Now, when you were identifying the endpoint before, we know that of a directed line segment in one variable, we only had to focus on one variable. But since we're in the coordinate plane, not on a number line, we know we need to know both the x and the y coordinate for the first point and for the endpoint. Since we were given the directed line segment ST, S came first. That means our S, negative 8, negative 4 here on our graph, is going to be represented as x sub 1, y sub 1, where T, 2, 5, is x sub 2, y sub 2. So why don't we go ahead and use these along with the ratio of 4 to 1, meaning A is equal to 4 and B is equal to 1, into our formulas. So A over A plus B would be 4 over 4 plus 1. So it would be 4 over 5 times x sub 2 minus x sub 1. That's going to be 2 minus a negative 8. And then we're going to be adding a negative 8. 2 minus a negative 8 is 10. So I'm taking 4/5 of 10, which is 8. 8 plus a negative 8 gives me a value of 0, which means point P is going to have an x-coordinate of 0. All right, so now let's go ahead and find the y-coordinate. Well, once again, I have A over A plus B. That's equal to 4/5. And we're going to be multiplying by y sub 2 minus y sub 1. That's going to be 5 minus a negative 4. And then we're going to be adding a negative 4 at the end. 5 minus a negative 4 is 9. So I have 4/5 times a positive 9 plus a negative 4. Now if I take 4/5 of 9, that's going to give me 36/5 or 7 2/10, 7.2. So this is equivalent to 7.2 plus a negative 4, which is going to give me a positive 3.2. So we have the y-coordinate as 3.2. And if we graph that, we see that's right here. So this point P divides our directed line segment ST into a ratio of 4 to 1. Now you use the formulas on your own. Let's look at another example for partitioning a directed line segment in the coordinate plane. Now I have the points A and B, negative 4, 2, and 5, negative 4 respectively, as endpoints of the line segment that we see graphed here on the right. And I want to know what the coordinates of point P are, such that P is 3/4 of the length of the line segment from B. The fact that it's from B tells us that B is the first point, so that's x1, y1, and then point A would be the second point, x2, y sub 2. And notice that we actually don't need to identify the A and B in this case because we actually already get that it's 3/4 from the starting point. So our x formula, we can just plug in 3/4 right there. So let's go ahead and continue. Well, x sub 2 minus x sub 1 is a negative 4 minus 5. And then we're going to be adding in x sub 1, which is a value of 5. Well, negative 4 minus 5, that's a negative 9. So we get 3/4 times a negative 9 plus 5. 3/4 times a negative 9 is a negative 27/4. And if I add 5 to that, that's like adding 20/4. A negative 27/4 and 20/4, it's a negative 7/4. Okay, so that means that it's going to be somewhere right about here. So we're actually looking for a value of P right there. Now it looks to be about 1/2, but you know what? Let's go ahead and use our formula. So y, once again, is going to be equal to that 3/4 that we found above. But now y sub 2 minus y sub 1. So that's 2 minus a negative 4. And then we're going to be adding a negative 4. Well, 2 minus a negative 4, that's equivalent to a positive 6. And then I multiply that by 3/4, I'm going to get 9 halves. So we can write that as 9 halves plus a negative 4, which is the same thing as adding a negative 8 halves. And that actually does give us 1/2. We kind of anticipate that's where it was going to be. Notice that P does look to be about 3/4 of the way from B to A. So that verifies the reasonableness of the answer. And so we know our answer, our partition, P, is at the coordinate point -7/4, 1/2. All right, so go ahead and think about this as you try this next problem on your own. So far, we've been answering the question, what does it mean to partition a line segment into a given ratio? And we used a formula to help us out. Now, what we're going to do is we're going to look at a special case, and that's identifying a point called the midpoint that actually divides our line segment into 2 equal parts. Let's use our knowledge of the section formulas in partitioning a line segment in order to develop a midpoint formula. Now, the midpoint is the point on a line segment that's equidistant from the 2 points. It means it gives us a ratio 1:1. Well, if we identify an a value of 1 and a b value of 1 from this case, we can plug that into our formula for x, and what that gives us is 1/1 + 1, or 2. So what I'm actually doing is taking 1/2 times the difference of x sub 2 minus x sub 1, and then adding x sub 1. So let's go ahead and use the distributive property. Multiply through, and we're going to get 1/2 of x sub 2, or x sub 2 over 2, minus x sub 1 over 2. And then since I have a denominator of 2 right now, let's go ahead and just rewrite x sub 1 as 2 over 2, because the coefficient is 1. That gives me 2x sub 1 over 2. And combining the numerators together, I'm going to get x sub 2 minus x sub 1 plus 2 times x sub 1 all over 2. And what that's going to simplify to, by combining like terms, is just x sub 1 plus x sub 2 all over 2. So the x value of our midpoint is the sum of the 2 x coordinates divided by 2. Well, we can use that same logic in order to be able to identify the formula for the y coordinate, the sum of the 2 y coordinates divided by 2. So we have a formula. The midpoint, denoted by m, is just going to be the sum of the 2 x coordinates divided by 2 for the x coordinate of the midpoint, and the sum of the 2 y coordinates of the endpoints, y sub 1 plus y sub 2 divided by 2, for the y coordinate of the midpoint. All right, well, let's go ahead and use this new midpoint formula for an example. Now remember, if you ever forget the midpoint formula, you can always refer back to the section formulas to help you out. Well, because it's a ratio of 1:1, it doesn't matter whether we start with A or B. The direction in this case doesn't matter. So I'm just going to let A be x sub 1, y sub 1, and B be x sub 2, y sub 2. So let's plug those values into our formula. Well, x sub 1 is a negative 4, and x sub 2 is 5. So we're going to add those two together and then divide by 2. And then y sub 1 and y sub 2, well, that would just be 3 added to a negative 2. And we would add those two together and divide by 2. Well, a negative 4 plus 5, that's 1. So 1 divided by 2, well, that's just 1/2. 3 plus a negative 2, well, that's also 1. And 1 divided by 2, once again, is 1/2. So we end up with a point 1/2, 1/2. Well, if I graph that point, notice that point M here, 1/2, 1/2, is exactly in between points A and B. Now go ahead and use the midpoint formula to try to find the midpoint in this next example. The midpoint formula is great because it allows us to identify an unknown endpoint. Now, first let's identify our midpoint formula again, just so we have it on here. We know that it's the x sub 1 plus the x sub 2 divided by 2 for the x coordinate, and y sub 1 plus y sub 2 divided by 2 for our y coordinate. Now we're given the midpoint at 1, 3. All right, so let's plug that in. Over 1, up 3. Let's be right there. And, in fact, put it in my coordinates here just for a reminder. And we know that the one of our endpoints, D, which I'm going to label as x sub 1, y sub 1, is at -6, -5. So over to -6, down to -5. That's going to be right here. So what we have here is a line segment that looks like this, but it goes somewhere, and I know the solution is going to be somewhere over there, but I don't know exactly where. So let's use the midpoint formula to help us out. Let's plug in the values that we do know. Well, we know the midpoint is 1, 3. We also know the x1 coordinate is a -6, but we don't know the second x coordinate. We know that the first y coordinate is a -5, but we don't know the second y coordinate. So what we can do is actually utilize this midpoint formula and set up two equations. 1 equal to a -6 plus x sub 2 over 2, and 3 equal to a -5 plus y sub 2 over 2. Because we know that 1 is the midpoint, the x coordinate of the midpoint, and 3 is the y coordinate of the midpoint. So let's use these equations and solve for the unknowns. Well, I can multiply both sides by 2 in the first equation. That gives me 2 equal to a -6 plus x sub 2. And by adding 6 to both sides, well, I'm going to get an x coordinate of 8. In the second equation, if I multiply both sides by 2, I'm going to get 6 equal to a -5 plus y sub 2. And adding 5 to both sides, I'm going to get a y coordinate of 11. Let's see if that makes sense. Well, if we plotted 8, 11, that's going to get me right here. Well, that's about where we predicted. If we draw in our line and look a little cleaner, does the point M look to be exactly halfway in between DE? It does. So we know our coordinate of 8, 11 is the other endpoint. So see if you can go ahead and use the midpoint formula to solve a problem similar to this one.